Hey Chitana, where is International Space Station? Hey Chitana, what is the keyboard of 175616? Hey Chitana, what is the South African equivalent of a barbecue? In this video, I'm going to walk you through how I use my voice to control this. Let's begin. Hey Chitana, bring us all back online. This is the split flap display. It's an electromechanical device made up of several modules that can show alphanumeric text and also graphics. They were popularly used to display arrival and departure information at airports and train stations, but they have mostly been replaced by LED display boards or monitors. Some YouTubers have made their own split flap display to use as counters, show text on a web interface, the time, or something else. And companies like Vesterboard and Old Foundry build split flap displays for cafes, restaurants, homes, and more. So why did I build this? I think it's a really cool project, and I wanted to understand how it works by building one myself. I also wanted to improve my 3D printing skills by printing and assembling something more complex. So you will see me make a few adjustments at some point in the video. Lastly, I wanted to make the display more interactive by using my voice to control what is shown. The split flap display module has a drum of flaps containing characters like numbers, letters, symbols, graphics, or a combination of some or all of these, depending on the application. The drum is connected to a stepper motor which rotates in discrete steps, enabling us to have precise and repeatable motion. Each revolution of a stepper motor is divided into an equal number of steps, and with this we can create a mapping to the flaps of the display. This means that rotating the motor a certain number of steps will show a particular character. The stepper motor is controlled through a series of pulses sent from a stepper motor driver, and the Raspberry Pi Pico microcontroller determines when these pulses are sent. We'll look at this module driver board, designed by Richard, shortly. The Pico needs a way to know the start or home position of the split flap display, to rotate the drum an exact number of steps to show a specific character. This is done using a Hall effect sensor, which detects changes in magnetic field. The Hall sensor finds the home position by detecting a magnet in the drum. This resets the motor steps to 0, which allows the Pico to accurately track how far the drum has rotated and what character is shown. A mechanical end step could also be used instead of a Hall sensor. For voice control, I'm using M5 Stack's Atom Echo, which has a speaker microphone combo. The Atom Echo listens for a wake word, as you might have guessed is Hey Chitana. This wakes Atom Echo up from its passive state to start listening for commands which are then transcribed. If a command or sentence matches one that was pre-programmed, an automation is triggered to output a response. This is sent to the split flap display through an MQTT broker to show the message. MQTT stands for Messaging Queuing Telemetry Transport, and it's a common protocol used for exchanging messages between devices, sensors, computers, and more. Afterwards, the Atom Echo goes back to its idle state. This is all done in Home Assistant, which is an open source home automation platform. Atom Echo is also connected to Home Assistant. On a side note, I got the idea for the flowchart structure from this video by Brian Poley. This is an overview of how the voice control works on the split flap display. I'll get into more detail later on. There's a README page in the project GitHub repo where I go into more technical aspects of the project. Now let's look at what we'll need. The first thing we need is obviously a split flap display. Mine builds on the work of 3 other projects. The most important one is from David, who made his design open source and provided a detailed instruction manual that walks you through how to build one. Dave Lamb reduced the original design from a 10-module display to an 8-module one, allowing it to be printed on an Ender 3. Finally, Richard designed this PCB or module driver that is compatible with David's design. The motors plugged in here are controlled by this motor driver, and the motors plugged in here are controlled by this motor driver. The 4 Hall effect sensors are plugged in here, 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 and here. We'll need more than one module driver for an 8-module display. Module drivers communicate with each other with these pins using the UART protocol. The motor driver is powered with 12 volts and is connected in a daisy chain with the other drivers to also supply them with 12 volts. I used 3 module drivers to control 8 modules. Then we have the Pico, which replaces the Arduino Nano using the original design. We also need a bench power supply to output 12 volts for the stepper motors, the M5 stack Atom Echo, a router or mobile device to provide internet access, and lastly, a PC to run Home Assistant. With the hardware sorted, let's set up the software for the split flap display. The Raspberry Pi Pico can be programmed in C, C++, or MicroPython. The split flap display code is based on Richards, which was written in MicroPython, a linear Python implementation optimized to run on microcontrollers and in constrained environments. The Pi Pico W is used on the primary or main module driver, which has wireless interfaces. This is needed to connect to the Wi-Fi network and also to communicate with the PC via MQTT. The other module drivers downstream will use the Pi Pico since they communicate using UART pins. We need to flash the Picos with MicroPython, and since we're using 2 different Pico versions, we need to flash 2 types of firmware. These are the steps of flashing the firmware onto the Pico, which I will demonstrate shortly. Click on this link to download the latest version. Download the latest version onto your computer. To flash MicroPython on the Pico, first hold on to the boot select button, then plug in the micro USB cable. The Pico will show up as a USB storage device on your PC. Drag the downloaded firmware file into the device to flash the Pico. Now it's ready to be programmed with MicroPython. What you'll do using Thonny, it's a Python Integrated Development Environment, or IDE. There are download options for Windows, Mac, and Linux. I already have Thonny installed and set up for Linux using Ubuntu. But before opening up Thonny, let's clone the product repository from my fork of Richard's repo, who was very helpful in solving some issues I had with the code and module driver connections. Click on Code and copy the HTTPS link. You can also download the zip version of the repo and unzip it afterwards. Now open up a terminal window. I'm going to place the repo in my downloads directory. Type in git clone, paste the link we just copied, and click enter. Now let's upload the code to the Pico with Thonny, which should immediately recognize that we're using MicroPython on the Pico W. Otherwise, you can click down here to change the interpreter. This section of the Thonny window shows the files on your computer, and down here shows the files on the Pico. I set this up previously, that's why I ran the downloads directory, but you can navigate to whichever directory you want. You can toggle the files view here in case it's not on by default. Back in the splitflap folder, click on MicroPython. While holding the Shift key on your keyboard, scroll down and click on this UART message file. Then click on the hamburger menu and upload / to copy all the files into the Pico. There are a few things we need to change in the main Python script. This conditional statement is used to check if we're using the primary panel with a Pico W or a downstream panel. At the moment, we're using a Pico W, so the network library will be imported to set up our wireless connections. Otherwise, we'll set this to false for a downstream panel. The last thing we need to configure are the panel elements. The panel represents the module driver. You can think of it as a section of the split flap display that controls a certain number of modules or elements. This panel only controls 2 modules, so only 2 characters can be displayed. The first number here is the general purpose inputs and output pin on the Pico for the Hall sensor, and the other 4 are GPIO pins for the motors. The remaining 6 characters are sent to the downstream panel with this line of code, and the elements are set up in a similar way depending on the amount of modules the module driver is controlling. Then the next set of characters are sent to the next downstream panel until all the 8 modules are controlled. Again, I go into more detail in the project README. We'll come back to Tony later, but now let's set up Home Assistant for voice control. Home Assistant is an open source home automation platform that prioritizes local control and privacy. With it, users can integrate over 1,000 different devices and services, perform automations with these devices, and visualize smart home information using dashboards. Your smart home system can also be extended using apps and can be controlled with your voice using the Assist voice assistant. There are more features which you can explore on their homepage. Home Assistant offers 2 different installation types: Home Assistant Operating System, or HAOS, and Home Assistant Container. HAOS is a recommended installation type. This is what we're going to use because we need to install some apps which aren't supported in Home Assistant Container. Apps are third-party applications that provide additional functionality within Home Assistant. You can buy a plug-and-play device like the Home Assistant Green, or check out these links for a DIY solution, depending on the hardware you have. After successfully installing Home Assistant, you can access it by going to this link in the browser tab. Home Assistant has its own voice assistant called Assist, which enables you to control Home Assistant with natural language. We'll configure our voice assistant to process our voice locally, but you can also do this in the cloud with Home Assistant Cloud. Assist needs to be able to listen, understand, and then respond to enable us to communicate to Home Assistant. An Assist pipeline will be set up to achieve this. The pipeline combines a number of components with these functionalities to create a voice assistant. Going back to our flowcharts, I've labeled the components we need to install. To detect our wake word, we're going to use the Open Wake Word app. We need a speech-to-text engine to transcribe our speech. We'll use the speech-to-phrase app for this. Custom Sentence is an inbuilt Home Assistant feature that can be used when creating automations. If the transcribed text matches our custom text or command, we can set something to happen. But this feature requires a working Assist configuration to run. We'll come back to the MQTT broker in a moment. These apps are provided by the Wyoming Protocol Integration for Home Assistant. Integration in Home Assistant are pieces of software that allow Home Assistant to connect to other software and platforms. So in this case, the Wyoming integration connects external voice services to Home Assistant, which we will make use of with Assist. Installing these apps in Home Assistant is as simple as clicking on the respective blue buttons on this page. Let's install the Speech-to-Phrase app. It took a while with my internet connection, so I'm going to skip to the end. Once that's done, click on Start. Follow the same steps for Open Wake Word. Whisper is another speech-to-text engine, but is slower than speech-to-phrase. Piper is a text-to-speech engine, which we don't actually need for our projects, but I installed it in the background later in the video to get feedback from the Atom Echo speaker. Now, we need to set up the Wyoming integration. Go to Settings, then Device and Services. We can see that Home Assistant already discovered the protocol. Let's configure the apps we installed by adding them. To create our Assist pipeline, navigate to Settings. Then click on Voice Assistants. I already have one configured, so we'll set up a new one with Add Assistants. Let's name it Split Flap Assistant. We'll leave the conversation agent as Home Assistant. Our speech-to-text engine is speech-to-phrase. To define the wake word engine, click on these 3 dots and select Add Streaming Wake Word. Scroll down to the new section at the bottom. Select Open Wake Word and leave the default wake word for now. Finally, click on Create. And with that, we've set up our voice assistant. These are the default Home Assistant wake words. I didn't want to use any of them to avoid possibly triggering someone else's voice assistant, so I created my own. Hey Chitana. It's pronounced Chitana, and it's an Igbo name that means remember father. The steps of creating your own wake word are outlined in this section. As a provided Google Colab notebook you can use to train a custom model for your wake word. The notebook is well documented, but you might have to tweak a few parameters a number of times until you get what you want. Once you've done that, you need to add your wake word to Home Assistant. Follow the steps in this section to do that. I've done this already, so let's go back to our voice assistant config. Your wake word should now appear in the list. Select it and update the assistant. Now, let's connect our Atom Echo to Home Assistant to turn it into our voice assistant. The M5 Stack Atom Echo is a programmable, compact smart speaker capable of audio playback and recording with its built-in microphone. It's based on ESP32 and it's able to stream media over Wi-Fi and can connect to other devices with these pins and ports. Let's plug it into our computer. The onboard RGB LED is used to indicate the connection status. Open this page in a Chromium-based browser. I'm using Google Chrome. Scroll down here and select on Connect. Look for the M5 stack in the device list and connect to it. Click here to install the firmware and confirm the installation. Click Next and add the Atom Echo to your Wi-Fi network. Then add the device to Home Assistant. It's going to prompt us to set up ESP Home, which is an integration to allow ESP Home devices like the Atom Echo to connect to Home Assistant. Click OK. Then click on the Atom Echo you discovered and submit. This process took a few minutes to complete, so I'll skip to the end. It doesn't show our custom wake word here, but it's not a problem. Let's go back and continue with the wizard. Skip, and skip on the area. Here we're going to choose Focus Local Processing. I had set the name as Atom Echo, so I'll leave it as that. We'll change our assistant to Split Flap Assistant, and select Done. Click on one device under the ESP Home integration. Scroll down here and change the wake word engine location to in Home Assistant. Leave everything else as is. Since we set up our assistant to Split Flap Assistant, our wake word should work. I installed the Piper text-to-speech app in the background so that we can test out our Atom Echo config. Let's go back to our test pipeline. Add Piper and update it. We'll use something simple to test it out. Hey Chitana, what time is it?
8:04 p.m.
We can use the custom sentence feature to create automations, now that we have a working assist pipeline. But we'll demonstrate that after we've configured MQTT, so that we can send messages to our split flap display. To review, MQTT is a protocol using message exchange between devices, sensors, computers, etc. It uses a publish and subscribe architecture, where a device, called an MQTT client, can publish a message on a topic to an MQTT broker, and another MQTT client or clients subscribe to the topic to receive the message. MQTT messages contain a payload with data to be consumed by the client. In our case, let's assume the output of our automation is a message hi. An MQTT client in Home Assistant publishes this message on the topic splitflap/commands. The payload here is a string message hi. The MQTT broker receives this and acts as a middleman by publishing the message on that topic for an MQTT client or clients to subscribe to. An MQTT client installed on the split flap display, which is subscribed to the same topic, receives a message and shows us what that is. This is all done on the same Wi-Fi network. We're going to install the Mosquito Broker app in Home Assistant. This also comes with an MQTT client the automation uses to publish our messages. Back in Home Assistant, go to Settings, Apps, Install App, and search for Mosquito. Click on Install, then start it. The next thing we need to do is to create a new user for MQTT. Again, let's go to Settings, People, Users, and Add a User. I'll use MQTT_broker as the display name. We'll use the same for the username. Input the password and confirm it. Toggle the local access only switch, then create. Next, we need to set up the MQTT integration to use the Mosquito app. Let's go to Settings, Device and Services. Home Assistant discovered the integration, so let's add it. Click on Submit. Once that is done, click on these three dots, then choose Reconfigure. Here, input the username and password you chose for the new user we just created. Then Submit. We set up the Mosquito Broker, which comes with its own MQTT client. Now let's install the MQTT client on the split flap display. We'll be installing this simple lightweight MQTT client called the MQTT using Thorny. At this point, make sure that you have the module with the PicoW plugged in because of its wireless functionality. This lib folder already has the MQTT client on the PicoW, but I'll delete it and show you how to install it. Go over here to Tools, Manage Packages, and search for umqtt.simple. Click Install. It's as simple as that. You can see another lib folder was created on the Pico with the client in it. The next thing we have to do is to connect our PicoW to the same Wi-Fi network and also set up the MQTT client to establish a connection with Mosquito. For the Wi-Fi settings, in the primary folder, open the wi-fi.py file. Down here is where you put in your network name and password. I'll quickly do that. For the MQTT client config, open this source mqtt.py file. This is the Python class I wrote that connects to the Mosquito Broker. Checks for messages from it and decodes them. Then loads the messages that will be shown on the split flap display. This is built on Richard's code that does all the heavy lifting of setting up the Wi-Fi connection, the UART communication between modules, configuring the stepper motors, and controlling them to display the message sent to the split flap display. Going back to the top, I set the MQTT client ID to split flap. We need to change the IP address, username, and password. We'll subscribe to the split flap command topic. The MQTT broker IP address is the same IP address for Home Assistant. We'll use this open source Angry IP Scanner app, which scans for IP addresses and ports on your network, and the different download options depending on the OS you're using. I already have it installed, so let's scan. So this is our IP address. Let's type that in. The username is what we chose earlier. Just put in your password. We finally got everything set up to start creating automations with our custom sentences. Let's go to the main.py file. Click Run. Down here we can see the IP address that was assigned to the PicoW by your router, and also confirmation that we're connected to Mosquito. Automations in Home Assistant allow us to automatically respond to things that happen. In our case, when a particular sentence is said, the response would be to publish a message to the split flap display via Mosquito. Back in Home Assistant, let's go to Settings again, then Automations and Scenes. Click Create Automation. We want to create a new automation. For our trigger, we'll choose Sentence. Underneath it says, when assist matches a sentence from your voice assistant, which is exactly what we want. Our sentence is actually going to be a question. which I think we've all thought about at varying points in our lives. What is the meaning of life? We aren't supposed to use any punctuation, so I'll delete this. And for our action, we want to publish the answer to that question on an MQTT topic. So let's search for MQTT and choose MQTT publish. Remember that our topic is split flap / commands. The payload here is the message we want to publish, which is also the answer to the question, 42. For quality of service, we want the message to be published exactly once. Then click on save. I'll name our automation Life's Meaning. Let's quickly confirm that Funny is still running. Alright then. Hey Chitana, what is the meaning of life? Something I didn't get into here was how to calibrate the motors to make sure that they show the characters we expect. But I detailed the calibration process in the README, which is based on a Python script written by Richard. The automation we just created outputs a hard-coded message, but I will show you how to create automation using LLMs after we've created an automation to know where the International Space Station is. The International Space Station, or ISS, is a pioneering laboratory that orbits the Earth every 90 minutes, traveling at 28,000 kilometers per hour or 17,500 miles per hour. For over 25 years, the ISS has hosted astronauts from all over the world that have carried out thousands of experiments which have led to advances in water purification, material science, medicine, and more. It also serves as a test bed for new technologies in life support systems, solar arrays, and robotics that will be crucial in building a base on the Moon and sustaining crews in long-duration spaceflight missions to Mars. The current plans are to keep the ISS in operation until at least 2030. This is where the ISS is at the time of recording. We can get its current location using this free Open Notifier API, which obtains the ISS location data from NASA. This API only outputs the ISS position as latitude and longitude coordinates, but we want to know if it's flying over a country or water body. This is where reverse geocoding comes in. Let's get an overview of how this is going to work. When a split flap display receives a message, "Where am I?" a function is called to obtain the ISS location, which starts out by getting the ISS coordinates. A request is made to the Open Notifier API, which subsequently requests data from NASA's database. Then a response with the ISS coordinates is sent back. The latitude and longitude we get are used to make a request to a reverse geocoding API service. Reverse geocoding is a process of converting geographic coordinates to a street address, while forward geocoding does the opposite by converting a street address to latitude and longitude. The API service requests the address data from its database, which is sent back to us as a response. This response is sent to a function in the main program to show the message on the split flap display. I chose to track the ISS location because I wanted to display real-time data. The reverse geocoding service I'm using is Location IQ, which also offers forward geocoding, maps, and routing services. It's a cheaper alternative to using what Google is offering, and their free tier plan is sufficient for our needs. You need to sign up to get an API key for the project. Once you've done that, you'll be shown your dashboard. Here, under reverse geocoding, we can see a sample request that takes in the API key, latitude, longitude, and format as inputs. And this is the JSON response. You can see that the address object is broken down into different key value pairs. We're only interested in the country key. To get your API key, go to Access Tokens, click on Show Token, and copy it. Then head over to Thorny to paste it in. Make sure you stop the main.py script if it's running, otherwise you won't be able to save any changes you make. The ISS location function is in the primary directory. This part of the code makes a request for the ISS coordinates. If you don't get any error, the response is used in creating another request to Location IQ to reverse geocode the coordinates to get an address. And from the address data, we extract the country. The API returns an error response with status code 404, where no location or places were found for the given input, which occurs when the ISS is over a water body. If any other error is encountered, that will also be printed with an accompanying error message code. Pasting the API key here. We can do a quick test to make sure that everything is working well. At the time of recording, the ISS is currently over the Pacific Ocean. Down here, I'm going to call the ISS location function and run this file. Right now it's over Argentina. Let's confirm if that's going to work. Let's run it again. Everything is working well. I'm going to undo this. Now let's create an automation to display the ISS location. First, we have to run our main script. Back in Home Assistant, we can just duplicate this automation we created, then make our changes. We'll change our sentence trigger to "Where is the International Space Station?" And the message we want to publish is "Where am I?" Save it as ISS location. Then let's test.
Hey Chitana, where is International Space Station?
The source MQTT class checks the MQTT message payload for these strings. "Where am I?", which is used to display the current ISS location. 8 spaces, which is used to reset display flap display to only show blank flaps. Then anything else that we hardcode, like the answer to the meaning of life, or a generated response from an LLM, which we're going to demonstrate now using the Home Assistant AI task. With the AI task integration, we can generate images and data in your smart home using an LLM. This can be with an LLM you're hosting locally using Ollama, or a cloud option from Google or OpenAI. I would have preferred running a local model, but my PC is extremely slow, so we'll use Google's Gemini to speed things up. Similar to Location IQ, we need an API key which we can get for free. In Google's AI Studio, click on the Get API Key at the bottom left, then on the Create API Key button. I'll leave the default name, then select Create Key. Click here to copy the API key to your clipboard. Now let's set up Gemini in Home Assistant. Under Settings, go to Devices and Services. Click Add Integration. Search for Google. Choose Google Gemini, then paste in your API key. We'll use the default name for the devices created. Click on Skip and Finish. By incorporating the AI task, the output of the automation is a prompt which is sent to Gemini to generate a response that is sent over to the display flap display via the MQTT broker. Let's demonstrate this with a simple automation. Here, let's change our sentence trigger to "What is the cube root of 175,616?" I found it easier to get a response when I spelled it out like this. We're going to add another action for the AI task. Click on AI task, then generate data. Name the task cube root of 175,616. Our instruction or prompt is in numbers only. What is the cube root of 175,616? I have to specify it this way so that we don't get more information than is necessary for our 8-module split flap display. Check the entity ID and select Google AI task. We want to save our generated response in a variable for our MQTT client to access. Here, under response variable, I'm going to use response. This action needs to be executed before we publish data with MQTT. So let's drag that up. Then in our MQTT publish action, we need to change our payload to this to extract the generated data from Gemini. I'll save the automation as cuberoot of 175,616. Make sure the main script is running. Let's test it out.
Hey Chitana, what is the cube root of 175,616?
We set up the split flap display and configure the Atom Echo to work with Home Assistant. We can now use a voice to trigger automation to show the current location of the ISS, a hard-coded message, or a generated response from an LLM. So what else could we use this for? This could be used in a school quiz to make things more interactive and fun when confirming quiz answers. For example, a geography quiz to name the capital cities of some West African countries.
Hey Chitana, what is the capital of Senegal?
Hey Chitana, please reset the display.
Hey Chitana, how about Liberia? Hey Chitana, and Mali?
Or maybe a trivia night to test your knowledge in different categories. Hey Chitana, what's the first name of the artist that sang Living La Vida Loca?
Hey Chitana, what is the South African equivalent of a barbecue?
And some supposedly controversial questions. I've been to Ghana and Senegal. I'm even wearing a Senegalese football jersey. But being Nigerian, the answer to this question is obvious. Hey Chitana, which African country makes the best jollof rice? I had some issues with the Atom Echo processing some of my commands, so I recommend using Seed Studio's Respeaker Lite, which performs better in the tests I've done and comes with a louder speaker. I use the Echo because it's easier to customize your wake word on it compared to the Respeaker Lite. This project might be out of Home Assistant scope, but the Apton integrations made setting everything much easier. However, I'm open to any suggestions you might have on how to make things more streamlined. The README has all the links I showed in the video, and others that I think might be helpful in understanding certain concepts. If you made it to the end, I hope you found this interesting. Thank you for watching.